All right, guys, so it should be recording now, and we're going to continue with the GPT and our discussion. So hopefully transformers are starting to make a little bit more sense. We're going to continue with the code and the next step, basically, right? So what we have left right now is loading the data. So we're going to go over loading the data, creating the tensors for train and test, and hopefully that'll make sense. And then after that, we need to get into the architecture, basically, right? So that whole diagram, all those blocks and everything, how that works. All right, so let's continue here. So I think the last thing that we looked at was we read the file, the text file. After reading the text file, we can look at the information about it. We can print basically the length, basically how many letters there are, but not unique letters. I just mean all the letters, even repeated letters. And then we use the function set, which allows us to look at unique letters, basically. All right, so this is the trick on how to get the alphabet that's available in your text. And this is why kind of everything is going to vary based on the file input that you put in. All right, so we looked at the length. We know these are basically the letters that are in one of those examples. And so you can see it's mostly uppercase, lowercase, and a few other things there. That gives us basically, I wrote here 65. That's the vocabulary size. However, when you're doing this, you're going to want to print this out so that you can make sure that that parameter is correct for your code. All right. So now the next thing that we're going to talk about is how to create our tokenizer. Remember that if basically last week, right, what did we do with Hugging Face? We always imported transformers, and then we would always say BERT tokenizer and BERT model. And then we would say BERT tokenizer dot from pre-trained BERT. And then we would say BERT model dot from pre-trained BERT, right? And we download those two things as separate things. That's how Hugging Face has implemented it. And basically that's a good thing because it allows us to think that there's the tokenizer and then there's the model, the neural network itself. The tokenizer, just think of it as a dictionary almost of IDs and letters. They're basically the vocabulary. Now these dictionaries or tokenizers are calculated from the text using something like sentence piece or BPE or something like that, an advanced algorithm. Llama, the last time I checked, was done with BPE. All right, so that's the algorithm they actually use. This code, however, is doing it manually. All right, so this should give you a good insight into how you can do this. Okay, so the tokens basically need to be converted to IDs. So that's what you will give to the transformer. You're going to give like a 17 or a 85 or something like that. And then that's going to correspond to a letter in the tokenizer. But in the transformer, that 17 is basically like a lookup. You're going to have a lookup table, literally, of the embedding for 17 once it's trained. It's vector of size 512. So we can use a dictionary and a reverse dictionary. This is a common thing because dictionaries are hash tables. And so it just makes it a really fast lookup to have the dictionary and the reverse of it. So when you're encoding, you look up the string to int. And when you're decoding, you look up what? The int to string. And it just, pretty fast. But it's basically the same thing, just inverted. So this is basically literally right there, the vocabulary of your tokenizer, and then you're going to need to have an encode and decode function that does this work. So here, for instance, we have the characters, right? So that's the characters here, basically. So we've got the list of characters. So we're going to enumerate it, and enumerate gives you a number and a letter, right? So then we have what we need. We have one and the letter and so on. And then here we do the exact same thing, but notice that the only thing is that they're, these are flipped. That's it. All right, so that creates the dictionary and reverse dictionary. So here we can print string to int, or we can print int to string. These are the two dictionaries. So you can see here, and that's literally what it is. I mean, you know, at the end of the day, you could code these tokenizers. There's no magic there. There just won't be as efficient as something that uses sentence piece, because those are nice and advanced algorithms. And remember, they create subwords. That's the trick, okay? Which we discussed already. So this is the dictionary that allows you to look up, you're encoding something. So you've got the letter A. Notice this is not complete, right? So it would be larger. So that it would take the letter A, uppercase, and it's going to give you the number 13. That's the thing that you will feed to the transformer. Okay, the initial input is that. Over here, we should have the reverse one, which is the ID, the int, and it gives you the string, basically. Okay, this is when we're decoding. So the GPT will produce a sequence of ints, and then we're going to convert that into our sentence, basically. That's what's happening in the underlying. We need to define, basically, the functions encoding. So an encoding tokenizer called encode. Notice that the architecture is called encoder and decoder, and the tokenizer also has encode and decode, right? And, you know, that's why it just rings of compression everywhere, right? So it's like, you know, but anyway. All right, so here's, you use a lambda function. So notice you can give it some input, S, and then that S, you can just iterate through it. So that's why we can give it a sentence, we can give it a word, we can give it a letter, a paragraph, whatever you want. As an input, this function will take it, no problem. It'll iterate through it, through every letter, and basically it just runs it through the dictionary S to I, which is string to integer, and basically it gives you an encoding. So once you create the dictionary, you can just invoke the function and give it its input. So in this case, you know, the sheep language, right? The famous sheep language. That's very used a lot in NLP. So encoding from the sheep language with the tokenizer, basically there's 4 letters. So the encoder gives this. And I think this is in the Jupyter also. That's an example. You don't actually need it in the Jupyter. It's just there for illustration. But notice it gives you 40, 39, 46, 46, because the H has in the dictionary the equal ID. We do the same for the tokenizer decode. To decode from integer to strings as follows. So in this case, I just grabbed these 4 IDs, right? And I fed them here, right? And so that's going to return then the decoded integers. So here you give it L, for instance, so for I and L, this is a list. And so you'd give that I into integer to string. So these integers will be converted into the equivalent string. This is just a join to create an actual string. So using the function decode for these values gives us our sheep tokens back, which are bad. Now we need to, okay, so that's the example. Now, something that you do need and happens in the code is to take the whole text and encode it, right? So this can be done in several ways, but this is a good approach to take the whole text here. So, which is the book. So remember that the variable text was basically the whole of Huckleberry Finn. Okay, so that's the whole of Huckleberry Finn, or whatever, you know, Harry Potter or something like that you're using. Or if you have all the works of Shakespeare, you know, that's all the works of Shakespeare. So you take in that into the encode function, and it's going to give you the integers, basically. Okay. Then that is still not, that's just a list, like a native Python list. So you want to then convert that into a torch tensor. All right. And so you do that with torch tensor and the data type torch.long. And that's basically it. So you can see that here, printing the encoded data in torch tensor gives us basically something like that. You know, a sequence of integers, but now in a torch tensor, okay? The next thing we need to do, and you'll see in the code, is that you need to split this into train and text, okay? So we're gonna do the split into train and text. And so you can just do something like slicing, which you learn in any machine learning course that you've taken. Should know slicing, right? Pretty common. So here, basically figure out whatever the cutoff is going to be for the data. And so you can take up to 90% for train and then 10% for validation, etc. Okay? Questions? All right. So that starts to get at getting the data. So remember, this is called in machine learning data wrangling. The reason being it's complicated a lot of the time, right? So it's something that we have data loaders for, right? You know, if you use a lot of advanced things in PyTorch, we always want to use data loaders, that pipeline. And we'd use that a lot, I think, in 520, right? So data loaders. So that's a nice construct because it makes things simple. This does not use that because it's, you know, shows things how to do them from scratch. The next step is to create a function to read the data so we can train the GPT. Okay, so, and we need to read it in batches. So this is the code to do that. This is the function that will actually be used by the GPT. But to better understand the previous function, I kind of made a little example here. Okay, so that's the idea. So let's go down here and just take a look. This is what you get. Okay, this is the, and then we'll work our way back. So basically you have X and Y. So you can think of it as you have a GPT, right? And it's going to receive X and Y, right? And that's how it's going to train. This is the teacher forcing. Okay. If you notice, we have batches of 4, and this is just so it's readable. Your batches are much bigger, like 64. And I didn't use 40 because then it becomes harder to visualize. So the only reason why this is 4 by 16 is so that we can actually view it there. All right. So this is a batch. So that means this is one input that corresponds to this output. So remember that when the transformer is training or learning, etc., it's correlating this to that. Do you guys see that? And when it looks at the second one, it's only going to correlate this one to that one, right? That's what it's doing. But we feed it batches because we want to be efficient, right? So we can give it 64 of these, but they're you know, that although they're affecting the neural network, the thing that the transformer is looking at is if it's looking at this one, it should look at that one here. So if you look at this data, what do you notice? Do you notice something there? If you look at this sentence, the first sentence for both X and Y, what do you notice about them? They're shifted. That's it. They're shifted. This is how you train a GPT, if you notice. It's basically almost like learning. If I look at 56, so, oh, sorry, I need to look at it in the other way, right? So we're flowing down, not up, remember. So the transformer gets this one and should predict that one, right? Because it's X and Y, so it's flowing in this from, you know, down. So think of it as this. If it sees 39, it should predict 56. Do you see that? Why? Because 56 is the next ID after this ID. Do you see that? So if you get 39, it should predict 56. If you get 41, it should predict 43. If you get 39, it should predict 52, and so on. All right, so that's basically the idea of how this works. And this is the teacher forcing. It's literally this same sentence just shifted to the right by 1. Okay. So this is how this is done with this code, this function basically. So this is the example with smaller values. A GPT is a very deep neural network. To train it, you need inputs X and outputs Y. Inputs and outputs are matrices of the same size, batch size by number of tokens, basically. Okay, and that's all you have to give it. Okay. So they are basically several sentences as rows, the batch size, with n tokens, i.e. 40 in this case. The same sentence is selected for X and Y. They are the same sentence, but Y is shifted by 1 from X. That's it. Okay, and so all you have to do is go to that text, the book, and find a sentence anywhere, right? Just think of it. That's like really nice, right? You've defined, or this is how this works. You have your book. Imagine it's all of Shakespeare, right? And so you go somewhere in there and you find, a sentence. And now you have to take the sequence. So the following 40, and you extract it. And that becomes one sample. That's your X. To get the Y, all you have to do is shift it by 1. So get the next one. Do you guys see that? And then you start to create all of them. So really, you randomly can extract sentences from the whole thing, and then you basically feed that into the network. Okay, so that's what this function will do here. Okay, just extracting, basically, if you notice, it just creates a list of random numbers, which are IDs in the text, and then it goes there and it just slices out that sentence, shifts it, and that's your input and output. Is that clear enough, or any questions about that? And you can run through this code, read through this or run this in the Jupyter, and it should show you basically that it's producing. This is actually where it's happening, right? So it takes the for I and X, and you can see it's just +1 here. So it's just shifting by 1. Okay. But anyway, this kind of summarizes the whole idea of what it's done. Okay. So it created the whole thing. So hopefully that made sense. Then we have the loss function. We'll come back to this, but this is just your standard loss function to remember it predicts something and it's going to compare it to the real, right? So that's doesn't change at all. So that's the same. All right. So the part that I kind of want to get into is this, which is the architecture of the GPT. So hopefully this is the last thing that we'll cover today. And then we can come back to any loose ends, or you guys can read on your own. But this is also pretty important. So the architecture of the GPT or decoder. As can be seen in the following feature, the decoder starts with inputs and that go in sequentially into the decoder layers, right? So that's basically what we need to create. All right, so the way that this is done is that you create an object called decoder layers with the things that go inside of it as objects as well, right? So we'll see that in a second. So we're going to have a class that's the whole GPT, and then that class will create or instantiate several of the parts. Like a decoder is an instantiation of a decoder class, and you just do that 6 times, okay? So that's basically the idea. We also need to have a class for the feed forward. So that means we have a class for this box. We have a class for this box. We need to have a class for what's inside the elements that are inside the decoder. I think it's like 5 different objects. And then you literally just, whenever you need them, you just call them and build that part of the code, okay? So each decoder layer has the exact same architecture and consists of something called a multi-head attention, feed-forward layers, and then there's all other tricks like batch normalizations, residuals, and dropouts. Some of these you know about, like the dropout. Residuals you may not know about, and I can mention that at some point. But residuals are actually really important as well. Remember that the encoder is not used in the GPT. So basically just this, all right? So you've seen this as a diagram. Now the next logical thing is to see this as the actual PyTorch code, right? That's what we want to take a look at. So that should be the most important thing. And here it is. This code that you see here, the following code segment, we can see the class to instantiate the whole decoder with all 6 decoder layers and the last feed-forward layer, okay? So this is it. This is what brings together everything, and then the rest of the code is just definitions of some of these parts. So you can see standard approach is to create a class that inherits the NN module. So again, if you took 520, you saw this all the time because we did this all the time. We had the standard init function and we had a standard forward function. Now, another function that gets added in generative models is this generate function, okay? Which basically does what? It calls forward. You see that? So you have init and forward, init and forward, init and forward. But now you also want to have a situation where you generate code. So you have a generate function that simply calls forward itself, okay? So that's basically, this is the GPT. So we have the init function where several things are initialized. And then really forward, I would say this right here is the magic. That's it. So that's the thing that if it's not clear to you right now, this is what you want to spend a little bit of time on. Like even print out this and print out the diagram and just kind of like tie them together. So this is this is that, this is this, okay? So this is where this is happening. So I've tried to point out a few things here, and I use the dimensions, right? Whenever possible to kind of illustrate the convention. If you notice at this point, maybe it's starting to click in your mind where the name transformer comes from. What are you doing essentially? You take a tensor and you transform it into what? Another tensor. And then you take a tensor and you do what? You transform it into another tensor. And sometimes you make a big tensor, sometimes you make a small tensor. So, but you're always transforming these tensors basically, right? So, you know, that's where the name comes from. All right, so here we can take a look at the different parts of the diagram. So we have here this line of code, token embedding. This is what takes IDs n by 40 and produces n by 40 by 512. That's it. One line of code does that. Remember that the forward function is sequential, right? So what that means is you get an input, which is IDX, right? Goes through, right? All the way, and what you get out of it is logits, the output. So here, IDX, if we go back to the diagram, is this here. Make sense? That's IDX. And then this part in the forward function that is logits and the losses is this part here, this box. You see that? So you're going through the sequence to get from an input and output. Okay? So notice one line of code, this line here, this is a comment, and this line here is just basically getting the shapes. All right? So basically, the IDX shape is going to be batched by 40. You guys see that? So what does that mean? You get a set number of sentences, all of size 40. You get that? Right? Then notice that IDX then goes into a thing called self.tokenEmbedding_table. Where is that defined? In the init function. What is that exactly? It is a very nice PyTorch construct for embedding. And that's all it takes nowadays to create embeddings. Okay, so we'll look at the init function in a second, but I think if anything, this is the most important thing that you need to understand. You know, map that graph to this code, basically. Notice that once you get that, the token you get this variable token embedding. Notice here, you're going to have an X that is basically the sum of token embedding and positional embedding. Okay? They basically are two tensors of the exact same dimensions. Okay? If you notice in this code, token embedding is not going through positional embedding. right? It's not, instead positional embedding is created. But what is positional embedding? Positional embedding is also a function, an object that is a construct of PyTorch. And it basically, whatever the dimensions are of this, it's going to create that too. But it's going to create it in such a way that the positional encoding will be there. So that's one thing that requires quite a bit of code. So we'll come back to that. But for now, just understand that by creating this and adding these two together, now you have also positional encoding in there. You see what I'm saying? So the tensor in X, after this, knows that the comes before cat and cat comes before is, and you need to have that in there. It knows the embedding. But as I said, understanding this is quite a bit. It uses some techniques like sines and cosines. It's like creates a grid, right? And it's gonna, because the sentence goes like this grid also kind of goes like that. And one way of understanding it is it's a function that's doing this. So what does that tell you? More I see here, more towards the beginning. The less I see, the less to the beginning. Do you see what I'm saying? You want me to repeat that? So if you have a sentence, right? The sentence goes in that direction, right? And it's like this. Then you also have this other of the same size where you create some kind of function. But that function can be higher in the beginning and it starts to get smaller and smaller and smaller. So if you see small in that, what do you know? It's towards the end. If you see high, what do you know? It's towards the beginning. And that is encoded in the other one to have the positional encoding in. And it's brilliant because it's somehow the transformer can look at one part and know, oh, this is towards the end. Oh, this is in the middle. Oh, this is in the beginning, just by encoding that information. But we will do an example of this one thing later as a separate thing, just for you to understand. Make sense? All right, so for now, then, that's this box here. Okay, so this box, token embedding, remember, people made into age, weight, height, right? So vectors of 3, or in this case, vectors of 5, 12. And then this one is, notice you just add the 2. So in this case, the batch size is 64, right? If you check, the actual batch size is 64. The number of tokens in the sequence is 40, and the embedding for each one is 512. So the size of this is BTE, or 64, 40, 512. At this point of the code, we are here, okay? We are here. Now, this is like 3 lines of code here. Literally, these 3 lines of code do all of this. That's amazing to me, right? So very elegantly, they do this. So if you notice, let's take a look here. We'll come back to the init later, but let's just look at, this is the architecture, okay? So you have basically something called blocks, which is going to be the 6 layers, one after the other. That takes in X's input and produces X. So what in that one line of code blocks, you just went through all the code here and here and here and here and here and here, all 6. That one line of code, okay? Does it. So we'll need to drill down into how that's done, but it's actually not that complex in the end. Remember, they are exactly this, every decoder layer is the same, and it takes inputs, and the inputs and outputs are of same size, n by 40 by 512. Okay, so now that X, notice, goes in here. Notice that this once again is BTE, so that's 64 by 40 by 512, okay? This X now goes through this LNF. This LNF, notice I wrote here, norm, it's what? A normalization. Remember I said in machine learning in 520, love scaling, normalization, right? That's what's happening there. It's called batch normalization because it only normalizes for the batch, right? It's not going to normalize over all the data. It's only normalizing over the batches of 64. And this is what's called batch normalization. But it's real. What is normalization? What is scaling? Who can tell me? You guys know this. What was normalization or scaling? What's an example of that?
Some features have a higher value in thousands.
Yes.
The features, the value is in 0.1.
That's bad for machine learning, right? So what do you want to do?
You want to higher values usually bring down to the lower values in the range of 0 to 1. So that,
yeah, exactly. That's normalization, right? And so batch normalization is just a fancy thing that sounds complicated to say we do this per batch. That's it. Okay, but machine learning loves that, right? And transformers have their architecture plus these little tricks here and there. Dropout, normalization, residuals. They're everywhere. And I think you guys in 520 are like, I think David, right? You just went crazy with that, adding stuff everywhere. And did it help or I can't remember?
I think it did.
Yeah.
I can't remember exactly what the results were, but
yeah.
I think it made sense.
Yeah, exactly. So it's just something you use. And then the last one, so notice X comes out here, and then X now goes into LMFFW head. Notice the name head, right? It starts to be that last thing that you add to the network to produce something. And that gives you the logits over here, right? And that's basically your prediction. So this LMFFW should represent this last layer here. Okay? So let me ask you this question. If a decoder and an encoder are the same, if you notice, they have basically this, the encoder and the decoder are literally the same thing. But notice that the encoder has no final linear layer, right? So this produces n by 40 by 512. So effectively, it ends there. Do you see that? Whereas the GPT or decoder has this additional one that will take an n by 40 by 512 and produce an n by 40 by, in this case, 65, because that's the vocabulary size. So if I ask you, let's say on the exam, I've never said anything else, but I just say, write the code for a BERT model. I just want the architecture from here to here. I just ask you, write me the code for that. I don't need to know like inside the layers, right? Just what would you do? You could literally just write all of this without that one. That's it. Do you see that? Because if you look in the diagram, the encoder produces an n by 40 by 512 after 6 encodings. That's what this produces. Literally after this. This is just a batch normalization. Whereas this one will take that n by 40 by 512 and convert it into n by 40 by 65 or n by 40 by 100,000, whatever the vocabulary is. That's so literally my point is if you know how to code the GPT, you already know how to code the encoder. You don't necessarily know how to code the BERT or train it because the BERT has an additional thing at the end, which is adding a head. I'll show you that in a sec. But coding wise is basically this. So notice here, B by 40 by 65, batch size by 40. And now you're once again not at 512 embeddings, but you're back at vocabulary. You want to make, that prediction of the ID, right? Yeah. Got it? Any questions on this idea? So hopefully this gives you a sense that this is the architecture. Just these lines of code here perform all of this in the architecture. Obviously, we need to drill down a little bit, and that's important, and we'll do that in a second. If you notice here, after that, what this is doing is basically, notice that this can take here what? It can take the data and also the targets. So what are the targets here? the training data. So remember it's predicting, right? But also you have the actual data. You know what I mean? You have the X and the Y, right? They're shifted. So you're getting that Y and you're getting the X. Is this clear for everyone? So this is the same. So IDX is X and targets is Y, basically. So if we go back over here, oops, sorry. IDX, right? Targets or labels. Yes, just shifted. This is important, right? This is what we always want to understand in deep learning, the inputs and outputs. So, sorry, that comes in here and here. The IDX goes through the network, comes out here called logits, and then what do you do over here? What do you do there? You see that? That's your loss. So the model predicts a vector, right? Yeah. And you also have the actual targets. You see that? And so you're going to compare the two. Logits is n by 40 by 65. Okay, so you're going to have in there basically the ID that you're going to need. So now targets is what? B, not N. B by 40, right? The IDs, correct? And logits also will have B by 40 because it needs to compare the two. But you have that after you go through this function. The logits, because this has predicted the value that you want. Does that make sense, guys? So basically, you give it the X, it goes through the model, it predicts the IDs, 17, 3, 5, 7, and you have the real IDs, 17, 5, 3, 11. So it's going to compare those and minimize the loss. So that's the standard deep learning to train the weights, right? So we want to minimize the loss. This is an important one, so I'm not sure if you guys have questions on this. But this is where the comparison is happening to update the weights, okay? Logits are the Y-pred, maybe if you remember that notation, are the Y-pred logits. So Y-pred and targets are the Y-real. And they're going into cross entropy. Notice that that's how you cross entropy you train a GPT, which you know how that works. Questions? All right, so hopefully that made sense. So now the key thing is let's drill down. Now we got to drill down. But this is nice because you already have all the parts working together. And so now you can just start looking a little bit under the hood. So in the init function, we've got basically the initialization of a lot of these things. Notice that the token embedding table is just this. That's amazing to me that, that's it. So Torch created a thing called NN embedding. TensorFlow has it too. And basically you give it it's basically vocab size by N embedding. So it's a tensor of 65 by 512. If I had a vocabulary of 70,000 words, what would be the size of token embedding table? 70,000 by 512. That's it. It's a lookup table. That's how you can think of it. It's like a very efficient lookup table. You have ID 17, extract the 512 embedding. You have ID 3,700, look it up, 512 embedding. That's it. But initially, this embedding table is empty. Remember, it's a neural net. And so the weights are going to be updated, right? So that when the transformer is trained, what you're doing is you're giving it an ID and you get that nice embedding to use. Okay? Okay, the positional embedding table is another type of an embedding, notice. And then embedding, block size embedding, and it'll just calculate the information of the positional embedding. So we'll come back to this later. Now, notice here, the object blocks is that. So notice it is just NN sequential, which has basically a list of blocks. If you notice this code, this is a list comprehension, right? So you guys know that's a list comprehension. All right, so what do we do here? Let's start there. In the list comprehension, I have a for loop. And I'm saying for in range n layer, right? How many layers do I have? What is n layer? 6, right? So it's 6 layers. So that means it's going to iterate 6 times. Why 6 times? Because we need 6 decoder layers. And notice that it's going to do what? Something called block. Basically, it's going to instantiate the class block, okay? And this class block should be each one of these decoder layers. You see, so this is block 1, block 2, block 3, block 4, block 5, block 6. So in the list comprehension here, if you imagine after this executes, what you should have in theory is a list block, 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 block. Think of it as if you had a class and then you instantiated, and you called it block 1, block 2. You have 6 blocks in there. Do you guys see that? Does that make sense? Now, here's the trick that to me is really nice. Do you guys remember NN sequential? In NN sequential, you did, like in CNNs, NN sequential is used a lot, right? You do CNN1, max pool, CNN, let's say NN.CNN, right? Max pool, NN.CNN, max pool, NN.CNN, max pool. But because it's in NN sequential, when you just have to do that and it's gonna go through everything in sequence. It does it automatically. Remember that? So that's why this code works, because it's like a trick almost, right? So it's almost like, oh, I don't know if I can write here. Oh, I can type. I didn't know. All right, so that's great. So I'm gonna type in here and imagine that, that's really, all right, so, you know, if you were defining an architecture, you could do something like nn.linear, right? nn.linear, and you would do 3, 5, right? And then what would you do? You just, I think there's a comma maybe, and then you do nn.linear, and what would that be? 5, 10, something like that. And then you do nn.linear. And let's say this is, let me start at 4 here. So this is Iris, the Iris data set, right? And this is the last layer. So what is the dimension of this one? Like 3, right? And hopefully you remember that by using NN sequential, you can code a neural network like this. You see that? And that's all you have to do. And this will assume that X comes, if, you know, X that comes in through here will go here, right? Then it'll go to the next layer, and then it'll come out of the next layer. You see that? And that's all you have to do. And the architecture is done. Make sense? That's NN sequential. So in a sense, you can do the same. You can do the same with this code segment here, because it'll, in a loop, it'll instantiate 6 blocks. And so you treat it like this, and so now it can go through all 6. And that's all you have to do. Elegant, right? It's very... does this make sense? Okay, perfect. All right, great. So this is something I really like, because with that line of code, we do all of these straight through, and we don't have to connect them or anything. But again, this is because we're using a slightly higher level API of PyTorch, and so on. Now, the next thing that we want to look, so now we have, because we have this NN sequential, we can go through all 6 layers. And we'll obviously need to define, okay, yeah, great, but what is block, right? So block, notice it takes in as inputs the embedding size and the number of heads. Okay, so we'll need to know that. And when we instantiate the block, it's basically the architecture inside each one of these decoder layers, which they're exactly the same. But we need to find that class, right? So we'll need to find that one. Now, notice that after this, we just do this one, LNF, which if you remember was this part, which was just a normalization. And we already discussed what a normalization is. Okay, so notice here, it's nothing more than layer norm, a 520 topic, right? So pretty much you were just going to do the normalization. And then here, this should be very familiar to you, right? What is FF head? Notice it's just a linear function of n embedding to vocab size, which means that n embedding is 512 to 65. It's a fully connected neural. It's literally the standard thing, right? That we always use when we build a neural network or a deep neural network in PyTorch, just that linear layer. See how nice that is? So basically, we've defined the init, we've defined the forward network, we've defined that an X goes in as IDX, logits are predicted, that's our YPred. We define that targets is our real. Now, you might ask why this none, because remember that this is both used for training and testing, right? So when we say none, then we're probably doing inference, we're just testing. And then we provide targets as for training. Make sense? So that's really all that's happening. If the cross entropy just compares YPred to YReal, and then, as you know, neural networks then minimize the loss. Very complicated and also very familiar, right? It's almost like it's a combination of something very complicated, but also something that's very normal, like that we've seen before many times. All right, so that's kind of it. Yeah, as far as the architecture, the overall one, and now we just kind of have to drill down a little bit into some of the block, right? I'll leave attention for next class because that's my brain will explode for that one, but we'll get to at least block, and definitely that hard topic I just want to address. At the beginning of class, not at the end. All right, so I think hopefully this makes sense. I mean, this is the init. We went over all the details of it. We went through the whole forward. That's the whole architecture of the GPT. And then here, all we have here is the generate function, which I would say the one thing, I mean, there's a lot of reshaping and cropping, but the one thing to notice here is this one. Self. So by definition, in these classes, NN classes, you have an init and a forward. Forward is like the thing, right? Because init is the constructor. So when you say self, think of it as you're saying self.forward. Do you guys see what I'm saying? So you're basically invoking the function that given some x's, it produces some logits, basically, which are the thing that you're trying to predict. All right, so here, when we invoke this self IDX, we're basically giving it the input x, and we're predicting the y. Okay, that's what's happening there. And this is the generate function, basically, that we're going to use to generate our text. Okay. All right, so this is kind of here. I just explained it. So if you guys, if it's reading, you can read through it, all the details. So we've covered all of this. All right, so this is now the encoder layer, right? Or the decoder layer. So you can see here, a decoder layer, one of these blocks, we want to look at it inside, right? So what's inside of it? Well, that's definitely this. Notice what's important here. N40 by 512 goes in, N40 by 512 comes out. This is a block. It's made up of what? Something called a multi-head attention layer. This is the key thing, the 40 by 40, right? And then a fully connected layer. Okay? So these are the two items that a block needs to somehow instantiate. Okay? So let's take a look at that. So here is the block. So notice class block. Okay? We're going to go back to the GPT code over here, and notice where we did this 6 blocks, we were invoking this, instantiating this block called, this object called block, and the definition of it, the class definition of it is this one here. Okay, that's it. And the diagram is this thing here. So you might expect that there's some kind of an input going in. It's expecting an N by 40 by 512. It's going to go through the multi-head attention, and then it's going to go through a fully connected layer. All right, so we can take a look at that. We'll take just finish with this today with this class block, and then I'm going to give you guys some time to discuss your homework or project. Okay, and then we'll continue this in the next class. All right, so here's the definition of the class block. If you notice, once again, it inherits an N module, right? We did this all semester in 520. It's got the 2 classic functions, the constructor and the forward function, okay? It takes in X, okay, which X is expected to be N by 40 by 512. And then that X, notice here, goes in. First, it goes into an ln1. Then the output of that goes into an SA, right? Notice there's an X plus self SA. Do you see that? Can anyone tell me what this is called? Notice this interesting thing. Here's my X, right? Usually we have an X that goes through some function and then it produces an output. But here we're giving it the X to go through this, and then we're adding it to the original X. Do you see that? Do you guys know what that's called? This is called a residual. This is actually one of the most important things in deep learning. This little X plus, itself through a function. In the past, for many years, people just did this. In the past, that's all they did. And what would happen? The models, as they got deeper, kind of crashed. They didn't perform well. This problem was called the vanishing gradients problem. A good way of illustrating this example is like this. 0.5 times 0.5 is what? 0.25? 0.25 times 0.25 is what? 0.624? 625? Okay. Shouldn't it be smaller? All right, so 620. Okay, all right, yeah. 625. So you can see already there's a difference between 0.06 and 0.5. It's getting smaller. If you keep doing that, eventually you probably end up with 0.00001 times 0.00002. Eventually, that's essentially 0. You see that? This is called vanishing gradients. This happens in very deep neural networks because you have so many matrix multiplications. The numbers start to get smaller and smaller, and eventually it's like, it's all zeros, the thing crumbles. The fix for that was this thing called a residual, which was basically, yeah, make this smaller, but maintain the original value. I think this was Geoffrey Hinton again, and basically this solved a huge problem. What problem? Well, think of it this way. Everyone says you need deeper neural networks to work. But if you make them deeper, the gradients would vanish. So then it was like impossible to achieve what you wanted. If you made it deeper, they vanish. So then you have to make them smaller. They don't vanish, but they're not as powerful. You see the conundrum there? And then when they came up with this idea of residuals, boom, they can get super deep. And then you have all that computing power. So that's it. That's the trick. And if you notice, it's implemented in the Vaswani paper and it's implemented here. And so that's the thing with the Vaswani transformer. It had so many fixes to so many problems, right? Super deep. Anyway, so hopefully that made sense. So if you notice, the forward takes in X. LN1, as you can see, what is LN1? Normalization, layer norm. Batch normalization, once again, another Jeffrey Hinton improvement, I believe. So then it goes into SA, does the residual, produces an X. That X becomes the input here, which goes into another batch normalization. Feed forward, notice that's probably a linear that you're so familiar with. And once again, residual to produce an X. N by 40 by 512 goes in. N by 40 by 512 goes out. That's a block. So again, that's this diagram over here. So that SA, what is it, right? And then what is that FFW? That's probably a feed forward. So if we take a look here, and we'll stop here today with the code, and I'll continue with this next time. Notice that SA is a multi-head attention. Do you guys see that? So now we have this class called multi-head attention, okay? And that's where the attention mechanism happens. I just want to have a better example for this, and I don't have any, like, I'll have to come up with something. But anyway, notice you instantiate this multi-head attention, which needs the head size and the end head. So this is the idea of, it's not just one attention, but 8 attentions, right? And I gave you the example already that it's because it's like 8 people thinking about a problem is better than just one. So they wanted to give it more power. So it creates 8 attention layers. But anyway, we'll talk about this one in the next class. But this basically, as you can see, takes in X, runs it through SA, the multi-head attention. You get that X that comes out, and notice that this one is just a feed forward, which is another class, but it's pretty much a linear layer. Okay, that's just a class. And you have the 2 batch normalizations. Any questions so far, guys? Is the GPT starting to make a little bit of sense? Okay, great. So let's end this, and just the rest of the time, let's just go over your homework and, where you are, and then I'll pick up with this next time. So we're almost at the end. So hopefully after this will demystify a lot of these transformers. Read through the document. As I said, hopefully, it's helpful for you to have it available. All right, so I will stop the video here. So I'm going to hit stop. And I'll end this.